In the last video, we talked about how we would actually find the average y value on a function. Or you can imagine this is like the average height of a function. And we came up with this interesting formula. Again, a really mind-blowing formula that related the area under a curve to finding the average height. So we're going to take a look in this video at examples 1 and 2 to see how exactly we can put this to use on some different functions. So we want to start by finding the average value of the function 1 plus x on the interval from 0 to 3. Okay, so if I was to use the formula up above to find my average value, or what we commonly just label as f with a subscript of average, I know that I'm going to take 1 over my b minus my a, and notice here that 3 is playing the role of b, while 0 is playing the role of a. So this is going to be 1 over 3 minus 0, and then I'm going to multiply by the area under this curve. So 0 to 3 and 1 plus x dx. Now, of course, if I want to finish evaluating this, I can see that I'm going to have to figure out what exactly this integral, this area under this curve, is going to be. And there's really only a couple ways that I have to tackle this. One approach that I could take would be to set up a gigantic, big, scary limit like we did in some of the previous sections, right? I could just start to try to calculate this out directly. Now, while I could try to do this, we saw in the last section that I could try to look at some integration properties to maybe try to make this a bit easier, right? Maybe if I already know an area similar to this, I can use that to help try to find this more quickly. And the last option that we saw at the end of the last section was to just see if what I'm working with, if the area that I'm trying to find actually is just a bunch of nice geometric shapes that I can easily find the area of using my geometry knowledge. So what we're going to try to favor in this section is this geometry approach. Just for the moment, this approach will be more useful because I've designed these questions to actually work much better with the geometry approach. However, if I had sufficiently difficult functions, I might have to use the original definition and try to calculate out one of these big scary limits, or go through the properties of integrals. So let's go ahead here and just try to focus first on what exactly this graph actually is going to look like. So I'm going to go ahead and try to sketch it out over here. I know that I'm going to end up with the function, again, 1 plus x, so I'm going to have a y-intercept up here at 1, and it's going to look something like this. And if I'm working on the interval from 0 to 3, I should be able to tell that at 3, I'm going to be all the way up here at the height of 4. And so the area that I'm looking for right now is this area, all the way back down over to here. And what I'll notice is that that actually does meet the appropriate criteria to be tackled with geometry. Notice I can actually take this region and divvy it up into two easy geometric shapes. Can you tell what they would be? Well, notice here if I drew a line directly across at the y value of 1, I could get a nice simple triangle and a rectangle. So instead of calculating this again using the big scary limit or integration properties, I'm going to go ahead and just deal with the area of my corresponding triangle, and I'll add the area of my rectangle. So that's what I'm going to work with here. So this is going to be 1/3, and let's start with the area of the triangle. I know that an area for a triangle is going to be 1/2 the base of the triangle, and how long it is, times the height. Notice here that my base is 3 units long, and the height of this triangle, if I'm at y coordinate 1 right here, and I go up to y coordinate 4, that's also going to be a height of 3. Then I can go ahead and see that the area of my rectangle is 3 units. Since it's 3 units long and 1 unit high, I'd have 3 times 1. So I just need to go ahead and actually compute this all the way out. I'm going to have 1/3. Let's see, this is going to be 9/2 plus 3. If I distribute right away, I can see that I'm going to get 3/2 plus 1, or I could rewrite this as 5/2 or 2.5. So what we're saying here is that my average y value is 2.5. Now if I look at the picture, I can actually kind of position on here where my average y value would be. My average y value is going to look to be somewhere maybe right around here. this is my average y. Okay? So this is again how this would work in this particular instance, and I've used this geometry approach this time since I had such an easy figure to work with. Let's try this process again here on example number 2. Again, I'm being asked to find the average y value for this function on a given interval. So I would start by saying that my f average can be calculated by doing 1 over b minus a, so that's 1 minus negative 1, times the area underneath this particular curve. So I can easily see here that this is 1 over 2 times, again, whatever this area would actually be. Now if I draw a picture of this area, I can see very, very quickly that this is actually going to be a picture of a nice half circle again. This is going to be the top half of a circle of radius 1. So when I integrate from negative 1 to 1, I'm just finding the area of a half circle. But since I know how to find the area of a half circle using geometry, again, there's no reason to have to use the big scary limit or integration properties. So I'm just going to go here and do the area of half of a circle. Okay, so this is just going to be 1/2 multiplied by, and the area for half of a circle is 1/2 pi my radius squared. Since this is a radius of 1, I'll just go ahead and plug in a 1 there, and now I can compute this as 1/4 pi times 1. Or you could just rewrite this as a single fraction, pi over 4. So my average y-coordinate on here is pi divided by 4. Notice again, if this is a circle of radius 1, the highest y value here is 1, and pi over 4 is going to be somewhere right around here. So this is up at the height of pi over 4. That's my average y value on the graph. So hopefully, again, this shows you how I can easily compute average values. The only difficult part in computing an average value is computing the actual integral. And sometimes we can use geometry to help with this. It's not that in every case geometry will be useful, but fortunately it was useful in both of these cases.